So for the next talk, we'll be back to the tabletop, more or less, and it'll be Holger Müller from Berkeley, who's going to talk about measurement of the fine structure constant and entanglement of masses, or perhaps he's changed his title. We'll find out. Peter, it's all yours. I'll give you a 5-minute warning.
Generically, I'll talk about atom interferometry and fundamental physics, but in particular, I'll talk about two results. One is a measurement of the fine structure constant, and the other is using atom interferometry with atoms held in an optical lattice and what you can do with it. Okay, after Jason's excellent talk this morning, I do not need to spend a lot of time in introducing atom interferometry. So let's just remind people that these are the trajectories of an atom on its way through an atom interferometer. The x-axis is time, the y-axis is height. The atom comes in at a time t0. There's a matter wave beam splitter in the form of a laser pulse to split the atoms between an upper and a lower interferometer arm. We use mirror pulses to move the interferometer arms back together, and then they interfere at the final beam splitter. Here's an actual picture of atoms in our lab. The interference fringes at that moment are such that most of the atoms are in the lower output, and if the phase changes by 180 degrees, then they will all be in the upper output. The phase difference between the two interferometer arms is determined by the Lagrangian of the integrated along those arms, and the laser wavelength acts as a ruler for reading out the interference fringes, leveraging the precision of laser frequency stabilization for the phase readout. I want to drive home one important point, and that is, where do interferometers get their enormous sensitivity from? They get it from the fact that the phase difference between the arms can be millions and even billions of radians, while a 1 radian change in the phase leads to an order unity change in the detected atom number, meaning a part per billion change, or even less, leads to a nearly 100% change in the detected atom number at the detector. To drive that home, I have plotted those interference fringes, the counted atom number as function of phase, to scale using Mathematica. And you see that we have to zoom in many, many times before we see the fringes. And this here is actual data taken by Keng-Yao Chang at Stanford many years ago. So this is not my data, and this is not even state-of-the-art data. And of course, as Jason has explained, in the future, everybody will be trying to make this even better. So interferometry gives you a long lever arm to measure tiny changes and convert them into a large change of a measured atomic population. What's it been used for? We've already seen that it's been used for testing gravity and quantum mechanics in the Stanford 10-meter atomic fountain. It's, for another example, been used to measure the gravitational constant big G by Guillermo Moutinho and Florence, and we'll be talking about the fine structure constant. What is the fine structure constant? Why is it important, and how is it measured? Well, there are two types of fundamental constants. The most well-known ones, unfortunately, are really only unit conversion factors. The speed of light has units meters per second, and it would be useless to remember its exact value for a physicist, because the numerical value would be completely different using different units. In fact, the theorists can get away with not knowing the speed of light in meters per second. They just set it to 1 by choosing appropriate units. But then there are fundamental constants that are the same in every system of units, and they are statements about nature rather than our measurement standards. The fine structure constant is one of those. Its value is 1 over 137 and change in any system of measurement, and it is the ratio between measurable quantities, such as, for example, between the Bohr level splitting and the fine structure, or between the rest mass of an electron and the Bohr energy. These are all given by various powers of the fine structure constant. Because the fine structure constant is important in all of physics, methods from all of physics can be used to measure it. This shows the situation of a couple of years ago. Measurements has been done by spectroscopy on myonium using neutrons. measuring proton magnetic moments and by the quantum Hall effect. But the most accurate of them all are either come in two flavors, either measurements of the electron gyromagnetic anomaly in Washington and Harvard by Jerry Gabriels, or measurements of the ratio of the Planck constant and the mass of atoms. Before I show you how to do that, here a little footnote on the International System of Units. The International System of Units has recently decided to assign a fixed value to the Planck constant. Okay, so in some sense, that would justify me saying that we're measuring the mass of cesium atoms and not just H over mcs. But fortunately, physics is independent of such semantics. Why measure it very precisely? Well, the fine structure constant and the magnetic moment is kind of a lucky case in physics. If the fine structure constant is measured, for example, by atom interferometry to extremely high precision, theory can calculate the electromagnetic moment to extremely high precision. And so we have a case where an accurate measurement, an accurate calculation can be combined and compared to another accurate measurement. So we have three ingredients here in this comparison between theory and experiment, and they are all enormously accurate. In some sense, this is the most precise comparison between theory and experiment in science. And why is it important? This graph shows you some of the contributions of the standard model, and really not just quantum electrodynamics, but the entire standard model to the prediction of G-2. There's, of course, the first 5 orders of quantum electrodynamics, but then there are the infamous hadronic contributions that are so thorny to evaluate for the muon. The weak interaction is only about an order of magnitude away from mattering. If you look at this, then the hope, of course, is that maybe we have overlooked a particle or a fundamental interaction. And if that's the case, then maybe an enormously precise repetition of this theory and experiment comparison can uncover the missing element. That's the hope here. We've all heard about the muon G-2 mystery. I will not say too much about it, but for the longest time, it looked like there was a 4 sigma or so discrepancy between the standard model prediction of the muon magnetic moment and the electron and the theoretical prediction. And this has recently, this measurement has been repeated at Fermilab, and the significance of the discrepancy is now stronger. It's 4.2 sigma, has been called one of the strongest pieces of experimental evidence for physics beyond the standard model. Vexingly, there is also a new theoretical result that claims to explain why the G-2 is on this side, and that opens up interesting questions of its own. Let's just say that a lot of interesting physics can be done. I should say that the electron, both theory and experiment for the electron is way more precise than for the muon because the electron is lighter. That makes it easier to evaluate some of these effects at high precision. But it is, I would say, equally interesting. All right, how do I get the fine structure constant from atom interferometry? I'm looking at this equation, parts of which are familiar to my students in my quantum mechanics class. This is nothing else but the energy of the electron in the lowest Bohr orbit. And as low energy physicists, we would write that as h times c times the Rydberg constant, whereas the high energy people would write it as 1/2 alpha squared MEC squared. Those two are by definition of the Rydberg constant the same. And I can solve this for alpha and use that to determine alpha from the ratio of the Planck constant to the mass of the electron. But that's not very well known, and the electron mass in kilograms is not well known enough to apply this. What is very well known is the ratio of the electron mass to the masses of atoms, thanks to the measurements of Klaus Blaum in Heidelberg and other people. If we can measure, therefore, if we can measure the ratio of the Planck constant to an atom mass and combine it with the ratio of the electron mass to the atom mass, we can solve for alpha and then make the theory and experiment comparison. How to measure H over M? Here's a Ramsey-Bordé atom interferometer in which one matter wave packet stays at rest, subject only to gravity, hence the line is curved, and another partial matter wave packet is kicked up, flies for a time t, and is then kicked back down. While these wave packets are separated, they accumulate a measurable phase difference that is written here, and the term of interest is this first term proportional to the recoil frequency. That's the kinetic energy of the atom's motion in hertz, and it's given by the Planck constant times the wave number squared over 2m. So if I know the wave number, then a recoil measurement will give me h over m as desired. Unfortunately, elegant as this scheme is, it is actually enormously sensitive to gravity, and one man's signal is another man's noise, right? Whereas the experiments that we've heard about by Jason are looking for this gravity term, we're trying to not measure the gravity term. Unfortunately, the gravity term is larger than the recoil term, so we have to find a way to suppress it. There are two ways. The first is to make the signal that we want larger, and we do that by large momentum transfer atom optics, as Jason has talked about, in particular by multi-photon Bragg diffraction, where the atom absorbs, for example, 5 photons from a first beam and is stimulated to emit 5 photons into a second beam, so that it receives overall 10 photons of momentum kick. Because the kinetic energy goes like the momentum squared, this doesn't just give us a 10-fold enhancement over a single photon atom optics, gives us a 100-fold enhancement. So that's very useful and gives us this factor of little n squared here. The second way to improve the situation is to cancel the unwanted gravity term, and we do that by what we call simultaneous conjugate interferometers. This lower atom interferometer is the one I've just shown. And then there's an upper atom interferometer, which is essentially an upside down version of the lower one. And by adding the two phases together, the gravity term cancels out and the recoil term doubles. So now we are ready to measure the fine structure constant without being limited by our ignorance of how strong gravity is exactly. I should mention that these interferometers are so sensitive that the standard vibrational noise in a lab makes it impossible to see interference fringes, but fortunately, the two can be correlated to form an ellipse. So the scrambled phase of the first interferometer together with the scrambled phase of the second interferometer form an ellipse. The stochastically varying phase due to vibrations determines which point on the ellipse we get in a particular run of the experiment, but the shape of the ellipse can be fitted to determine the needed differential phase. A final ingredient is necessary to improve the sensitivity of the interferometer sufficiently, and that's Bloch oscillations at the center that are used to accelerate the upper interferometer further up and the lower interferometer further down. That increases the phase and so that it looks like this equation at the bottom. And the nice thing is the number big N of Bloch oscillations can be made very, very large so that the resulting signal is very large. Another nice thing is that the number of Bloch oscillations can easily be varied, and we can use that to repeat the experiment at various numbers big N to look for systematic effects. Here's what the setup looks like. It's a standard atomic fountain. It does indeed fit on a tabletop. Its height would, in theory, enable us to use a time of flight of up to a second, but in actual fact, we never do that. The reason for that is that the systematic effects go up with time of flight faster than the signal we're looking for. Signal we're looking for is proportional to t. The signal from gravity gradients is proportional to t cubed. So in actual fact, we never fly the atoms for longer than about 200 milliseconds. Here's some data. When we measure alpha, we scan through pulse separation times from 5 milliseconds to 80 milliseconds. And fitting that to the expected phase as function of time of flight gives one determination of alpha, and then we go through that for days and days and days. 1 day of data roughly gives one estimate of alpha, and in the end they are combined to a global average. Going through these in real time allows us to spot misalignments of the setup that would give rise to a deviation of the expected behavior as function of t. Okay, it's very important in precision measurement to not be biased by knowing, by comparing your data to other people's data. We therefore adopted a blind analysis. And even after we were done with the error budget, I will talk more about the error budget later, so I'll skip this slide for now. Even after we're done with nailing down all the terms in the error budget, you still repeat the experiment over and over again and look for variations of alpha with all sorts of variations. For example, you run the experiment with a lower contrast on purpose and see if the value of alpha shifts and so on. And only after you're satisfied that all these experiments either yield no variation of alpha or they yield a variation of alpha that you understand quantitatively and that you can take out, only then you unblind. And when we unblinded, the result looked like this. So let's look at only the 3 most recent. This is the previous atomic physics measurement of alpha, 0.66 part per billion accuracy. This is G-2, 0.24 part per billion accuracy, and this is us 0.2 part per billion accuracy. You see that we are fully compatible with the previous atomic physics measurement, but there's a 2.5 sigma discrepancy from G-2. And I would say the bottom line, the 0 order message here is that 2 numbers determined by completely different ways agree to the part per billion level of precision, which is great. But we're curious and we want to know what could the 2.5 sigma be due to. Well, first let's put it in context of the standard model theory. These lines are the current accuracies of G-2 and alpha, and you see that the accuracy is good enough to see the contribution of the muon at about 10 sigma, to see the 5th order QED effect at a couple of sigmas, and to see those hadronic shifts that are so thorny in the muon measurement also at about 10 sigma. But we're still an order of magnitude away or so from seeing the tau and from seeing the weak interaction. The 2 discrepancies between muon and the standard model and the electron in the standard model can be plotted in common coordinates. And then if you look at how good a job does the standard model do at predicting lepton magnetic moments, you find that the standard model is about 5 sigma off, which is actually quite a lot. The signs of the discrepancies for the muon and the electron are opposite. And so there have been theory papers, and this is way above my pay grade. I just mentioned that for completeness. There are theory papers that say, here's a model that explains both discrepancies. And there have also been theory papers that argue that the 2 discrepancies must have different reasons because they have different signs. Anyway, future of alpha, what to do from here? Well, one important element of the future, or of the present actually, is a new measurement done by the Paris group, the same that, whoops, what happened? The same that had measured this data point here, okay? And they now find a value of alpha that is slightly to the right of the G-2 derived value. We can speculate for a bit why that might be, and it could have to do with the fact, with the way the laser beam is prepared. But on the whole, I would say they did a solid job here. There is nothing where I would say, oh, this is the reason, obviously. And in science, what we need is not speculation, we need data. So we want to improve the measurement of alpha even further. I will say one thing. When our experiment and their experiment were constructed, scientists did not understand the imperative to create very clean speckle-free laser beams very well. And so our new experiment will be the first experiment that has been constructed from the ground up to create an extremely pretty laser beam. And now let's look at the error budget. A large number of error terms, for example, the Goi phase, wavefront curvature, and so on, scale with the size and smoothness of the laser beam. The more close the laser beam is to an ideal plane wave, the better. So all those terms in the error budget can be dealt with by making the laser beam larger and cleaner. Other terms in the error budget, such as the gravity gradient, can be dealt with by better characterizing them. And so even though there's a large number of terms in this error budget, we expect that a new experiment can address many of them at the same time, and we're ready for an order of magnitude improvement. This is how it looks like. We have constructed and recently baked a large diameter vacuum chamber that is very suitable for giving us a clean laser beam because it minimizes scattering of the beam at the walls. There's a new atom interferometer geometry to cancel the gravity gradient, and we're working on a several 100-watt laser system to fill the enormously thick laser beam in this chamber with intensity. With that, I want to close the fine structure part of this talk by thanking the people working on it. Zach Pagel, Matt Bernstein, and Jack Roth are grad students. Yeri Segev is a postdoc who has recently joined us from Weizmann, and there's a host of collaborators, previous people, also collaborators at Lawrence Berkeley National Lab that I'm indebted to. Before I close, I want to spend a few, how much time do I have from here on?
Let's see, if you could finish in 7 or 8 minutes, that would be good.
Okay, I'll try to make it 7.5. I want to talk a little bit about a new paradigm in atom interferometry, where we will not measure things by dropping atoms, but by holding atoms. So I'll talk about cavity interferometry. Let's build an optical cavity around the atom interferometer. What are the benefits we get? We get higher laser intensity, we get smoother and more well-defined laser beams. So let's try that. The cavity is actually very pedestrian. It's about 40 centimeters long and has a finesse of only about 100. The reason is we want the cavity to act as a good mode filter, but we want the line width to be large enough so that we can still drive Raman transitions and Bragg diffraction without trouble. Okay, and the sweet spot is at a finesse of about 100. This is how the machine looks like when it's finally assembled. This is Vicky Shu. She's been grad student on this project, will now join the LIGO group at MIT as a postdoc. And what can you do with that? Two applications I want to mention briefly. The first is we've used the machine to measure a force induced by black body radiation gradients. If there's a hot object inside your vacuum chamber, this metal cylinder heated by a laser from outside, even at 100 degrees C, it emits black body radiation. Most of the black body radiation is redly tuned with respect to the atoms, and the gradient of that causes an attractive force of atoms towards the heated object. This was stunning to us. With hindsight, of course, it's completely clear that this should be expected. What's stunning is that this causes microns per second squared accelerations, which is thousands of times higher than the intrinsic sensitivity of atom interferometers. And so this shows if you actually want to measure gravity very precisely with atom interferometers, you have to control the temperature of your vacuum chamber very well. A second application is detecting fifth forces caused by exotic theories of dark energy, for example, the chameleon particle. And you can see that we have repeated this experiment twice, and each time had about a factor of 100 improvement in sensitivity relative to the previously known limit. Okay, but let's move on. How can we use cavity interferometry to realize long interrogation times? I don't need to spend time to talk about very long baseline interferometers such as this one on construction in Hanover, or the one in Stanford. There's also efforts to run atom interferometry in free fall on the space station because long interrogation times are good. But you reach a point of diminishing returns. What if you want to hold the atoms 10 seconds? You would have to build hundreds of meters tall. Or maybe we can hold on to the atoms. And this is an idea indeed that was first realized by others in 2012 and then repeated by the Tino group, and they got a hold time of up to 1 second, limited by the inhomogeneity of the optical lattice used to hold the atoms. And so we thought, great, we have a very homogeneous laser beam in the optical cavity, maybe we can improve on that. And so here's what we do. The atom starts like a standard Ramsey-Bordet atom interferometer, only now we use the cavity mode as a beam splitter. Then when the atoms are at rest, we turn on an optical lattice where we store the atoms for a while. And then we turn the optical lattice off and repeat the beam splitter sequence to bring the two partial wave packets to interference. And here are some interference fringes that we obtained early on. The phase difference, actually, unlike the standard atom interferometers, the phase difference in this atom interferometer is almost completely determined by the free evolution phase during the lattice hold, which is essentially given by, well, the difference in the action between the two paths. And I will note that, curiously, it is proportional to the proper time difference between the two locations. And then let's see if we can gain hold time. So a fringe after 0.2 seconds still has 80% of the theoretically expected contrast. After 1 second, it's going strong. 5 seconds, contrast starts to drop a little bit, but not too much. After 10 seconds, contrast has dropped further, but the fringes are still very clearly visible. In the first talk I presented that ever, I presented this in real time. So now we're at about the 15-second mark. And finally, we could demonstrate interferences even after 20 seconds. So here are two spatially separated wave packets held separated by the optical lattice for 20 seconds, and you still have fringes. One practical aspect why this is a good thing is that in a standard atom interferometer, you flash the laser on at 3 or 4 times, and only in those times do the atoms interact with the environment. Meaning if you have time-dependent perturbations, such as vibrations, you're going to alias them, and you have way more noise than you should have. But thanks to the lattice hold interferometer averages over those vibrations. And so if you plot the vibration sensitivity as function of frequency, you will find a very strong suppression of the unwanted sensitivity to vibrations. We have demonstrated that with data. Unfortunately, the data is not shown here, but it matches the theoretical curve beautifully. The current state of the art is that the contrast decay is the slowest for very small spatial separations and is faster for longer spatial separations. And a model generated by my postdoc Chris Pander explains that as a result of atoms thermally orbiting in the lattice potential. I won't have time to explain that in detail. So in the future, we'll try to make this better, longer holds, better contrast, and then we can either use that as a compact vibration insensitive gravimeter. We can try to measure gravity of smaller masses to explore gravity at smaller scales. We can go for a gravitational Aharonov-Bohm effect and try to show that there's a phase difference generated by gravity in the absence of classical forces. And finally, and this is an idea that really is due to Jake Taylor and Dan Carney, we can try to answer the old question: if I have an object in a superposition of being at 2 places, which way does the gravitational pull from the object pull? is the gravitational pull also in a superposition? If the answer is yes, then that would show that gravity is a quantum field. Or is it not? In which case gravity would be classical, whereas all the rest of the world is quantum, and that's a very strange prospect. You can find the details in this preprint by Jake Taylor and Dan Carney. For now, I want to thank the people working on the cavity atom interferometer. Here's some of the people of the early hours. Matt Jaffe, he's now a postdoc at University of Chicago. Vicky, I mentioned. Chris Pander is the postdoc right now. Logan used to be our postdoc until he got lured by the green pastures in finance. And James Egelhoff is now a grad student. Miguel and Andrew are undergrad students. Thank you very much for this fantastic workshop and for listening to my talk.
Well, thanks for a great talk. You presented a lot of results and a lot of future directions as well. So what questions, what comments, what suggestions do we have? Let me ask one. Can you speak more about future plans for doing the classical versus quantum gravity experiment, the last one you mentioned on your previous slide?
Yeah. So this is an idea that is obviously not our idea and has been talked about at the very least since Feynman. But the elegance of this new proposal, and I'm bragging about it because it's not my own idea, I just claim credit for it, right? If I misrepresent it, Jake Taylor is here and might be able to correct me. But the idea is this. If the gravitational interaction is capable of generating entanglement, and that is a question, not a statement, because classical gravity, such as described by general relativity, is not, right? If that's the case, then I can use it to entangle. I have an atom that's in a superposition of being in two places, and I can entangle that state with the state of a classical harmonic oscillator close by using gravity. I could try to demonstrate this entanglement by conducting both measurements on the atom and measurements on the harmonic oscillator, but the scheme described in this preprint shows that it is not necessary to do both measurements. You can prove the existence of entanglement by showing that the atomic interference fringe has a modulation in visibility, in particular this collapse and revival of the interference fringes.
Yes.
Now the contrast is not very large. It is determined by the strength of the gravitational coupling. But, and this is the other great idea of Taylor and Carney, it can be enhanced by running the interferometer at a high temperature. This is an unintuitive result, and I spent a lot of time verifying it, and I'm convinced that this is right. And it can be enhanced by, let's say, biasing the interferometer by generating an initial entanglement using non-gravitational forces, because now we have an effect that's linear in the gravitational coupling string. You're welcome to ask follow-up questions, but I'll leave it at that for now.
Yeah. Why don't we go to Andy, whose hand has been up?
Hi, Holger. Very nice talk. So I had actually a question on the same proposal. So I just wanted to get a sense for what kind of separation distances you're imagining between masses and things like that for this quantum gravitational test.
The one sentence answer, but don't worry, you'll get a second sentence too. The one sentence answer is smaller is beautiful. But the key experimental challenge is how close can I get the harmonic oscillator to the atoms without screwing up the performance of the atom interferometer. And the limitation here that I can see right now is really that anything close to the laser beam will cause optical diffraction, and that will mess up our beautiful optical lattice. Also, if that messing up of the lattice is dependent on the position of the harmonic oscillator, then this alone will generate an effective interaction many times stronger than gravity. So there needs to be some sort of shield between the mass and the atoms. And I want to put in a plug for a beautiful result by one of my former postdocs, Xiaoyu Lan, who's working at Nanyang University in Singapore. He realized an atom interferometer inside a hollow core optical fiber. So that shows that at least in theory, such a shield is feasible even on a small length scale. So to make the experiment happen, we would try to see how close can we get the oscillator to the atoms and then go from there. All other dimensions, like the optimum splitting between the wave packets and so on, scale with that distance. But I want to mention one feature of the signal here. It goes like the whole time of the atoms to the 4th power. Okay, so by having 20 seconds, we have already come a long way to making this term big. And by even improving the 20 seconds by just 50% or maybe doubling it, that would make the signal a whole lot larger too.
Okay, thanks.
Okay, Anupam.
Yeah. Thanks, Holger. Very nice talk. And I just wanted to touch upon the last point, what Andy asked. So if I recall from our paper, which Andy is also involved in, I think we would require masses roughly of the order of 10 raised to minus 14 kilograms. And you have to create a Schrodinger cat state with a separation roughly around microns, so 100 microns. Now, then only you would get an entanglement phase due to gravity would be roughly of the order of 1. So, so that's the reason I think perhaps Andy was also asking this question, that what exactly the Schrodinger kitten state you want to create and how massive your system should be and how long will you be able to measure or observe the entanglement phase to make it something somewhat observable. Maybe
so the answer to all these questions is there is no safe approach here. There is no separation. There is no duration that I can promise that would make the experiment definitely feasible. All these parameters have to be improved relative to what we can do now. The preprint outlines a scenario assuming hold times of around a minute with splittings of around 100 micron, where the numbers do work out. And I should say this gives rise to a visibility modulation less than a part per million, so it's barely measurable, right? But even if these numbers sound scary, the reality is more scary still, because, for example, while we have demonstrated 20 seconds hold time, so that 60 seconds doesn't sound terribly much longer, right? That has all been done without any objects close to the optical lattice. So getting the same hold times and extending them will get a lot harder with the needed kind of shielding.
And by any chance, did you also study the decoherence rates and how cool the system has to be?
Yes, and I had a slide that I showed only very briefly. So here's the measured contrast as function of hold time for various separations. And here's an outline of the model. Imagine that the optical lattice is a pancake-shaped potential. So imagine you're a partial wave packet in one of those pancakes. Your temperature isn't 0. You have a kinetic energy, and so you describe one of those orbits inside that potential, right? Orbits could look very complicated, or they could simply be circular. And your partner partial wave packet in the lower pancake is describing a similar orbit. If these two orbits separate too much from one another, then upon interference, the contrast will be very low. And so this model does a good job at explaining these curves, and it also points out what we need to do in order to improve things. Even more smooth optical lattices will obviously help. And what will also help is to make the two pancake potentials more similar to one another by putting the thinnest part, the waist of the laser beam, in the middle between the two wave packets and not to the side. I'm sorry if I'm not very quantitative here. Maybe Chris is in the audience and he knows those numbers.
Don't worry, it's okay. It's okay. Thanks. Thank you very much.
Sure.
Yeah, John March Russell, you had a hand up. Do you still have a question or suggestion?
No, it was exactly the same question as Anupam asked, so
okay.
that was fine. Thank you.
Yeah. Okay. Any more on Holger's talk or related things?